So let's get started. Welcome to the Introduction to Deep Learning for Computer Vision workshop. This workshop is quite recent. It's been published in the workshop library in the end of last week. And in this session, I will walk you through like how to organize this workshop and through the content of the workshop. And I hope that some of you will then want to run this workshop in your university. So the idea of this workshop is to introduce people to both deep learning and to computer vision, to take the problem, which is like a quite interesting problem for computer vision, and see how neural networks can be applied to solve it. So here is the problem. Suppose we are having the pet care center, which receives different animals, different cats and dogs, and we want to be able to prescribe them certain medicines based on their breeds. And that's why we probably want to be able to recognize the breed of a cat or a dog from the picture. Because that's not an easy task, right? Even for a human being, it's difficult to do that. But we want to train to make an application to do that. So how can we do that? That's a very typical computer vision task, which is called image classification. And we know that neural networks are often used to solve the problems like that. And to train a neural network to recognize anything, we need the data set. So luckily, there is a data set which we can use for this problem. So let's see like what we need to know before we start. Ideally, this workshop will teach people about neural networks in general, about different computer vision tasks, and about particular type of neural networks called convolutional neural networks. And we will solve the practical problem, recognize cats and dogs from real-world images. What people need to know, ideally they want to know some Python. It's not like hardcore coding, but for all neural network trainings, typically people use Python, so it's nice to know Python. And ideally, they should also be familiar at least a little bit with PyTorch or TensorFlow framework. However, that is not strictly required because I believe that in 1 hour it's possible to introduce the basics of the framework as well. So in Microsoft Learn, we have something called TensorFlow Learning Path or PyTorch Learning Path, which contains several modules. And the first modules are introductory. So if you plan running this workshop like at a certain time, you can say that people should go through those introductory modules before the workshop, and that would help them understand things much better. Alternatively, I have prepared also a short blog post, which is here on the slide. And this blog post is a quick introduction to neural networks. So I will show you briefly how it looks. So it starts from the very basic, what is machine learning, then comparison between different neurons, artificial and real neuron, tensors, PyTorch, TensorFlow. So the very, very basic things you should know. And that's a good alternative to going through the whole introductory learn module, because that can be done faster. Also, what you can do, you can go and make the introduction a part of the tutorial as well, because it doesn't take a long time to introduce people to neural networks. So let's actually go ahead and do that very quickly. Like, what can you tell people about neural networks for those people who don't know anything about them? So neural networks, they are inspired by our brain. In our brain, there are a lot of primitive cells called neurons. Well, they are not actually primitive, but if we try to create a model of them in the computer, the model turns out to be quite simple. Each neuron is represented by an element which has several inputs and one output. And this element just adds together those inputs with certain weights and carries out the signal to the output, applying some also nonlinear activation function, because the way neuron works is that when the input signal is above certain threshold, it kind of fires, and before that it does not. So that's to model that we use activation function. And mathematically, this is represented by just the weighted sum. So we multiply each input by the weight, add all of them together, and that's it. If we have several neurons, like suppose we want to classify a cat versus a dog, then input would be pixels from the original image, and outputs would indicate whether it's a cat or a dog. So we would have, in this case, we might have two outputs. And to model a situation like that, like when we have two neurons with the same inputs, but the weights would be different. So this can be modeled by a matrix. So instead of having separate number of separate weights for first neuron, separate weights for second neuron, we can write weights as one matrix here and multiply it by the vector input. So in vector form, this would be very simple thing, like the output of the network Z would be equal to WX plus B. So linear equation if we take it in the matrix form. So that's why what we need to do to train neural networks, we need to be able to operate on those kind of matrices. But sometimes we need a little bit more than that, because neural networks, they are often trained on GPUs, and GPUs, they are capable of parallel computations. That means that we can multiply a lot of matrices at once. So normally we would want to put several training samples to the network and receive several outputs all in one computation. So that is called mini batching. So suppose we take like 9 inputs, which is represented here. Like we take 9 inputs. Sorry, I'm trying to draw on the slide, but that doesn't work anyway. So we have 9 inputs. In this case, we can still multiply 9 inputs by the matrix, and we will receive 9 outputs as a result. If you take the Python, any Python library which operates on matrices, like NumPy, it supports this automatically. Like you can take the input size 9 times 3 times 1, so that would be this vertical vector of x's, and multiply it by a matrix 2 by 3, and you will get output 9 times 2 times 1, which is the 9 outputs for the 9 input cases. So that's actually means that to train neural networks, we would operate a lot, we'll multiply a lot of matrices. So so how does this work in practice? So suppose we have inputs, like we have several inputs, x1, x2, x3, and maybe more. If it's a photograph of a cat or a dog, definitely there would be many more inputs, and certain number of outputs. So those outputs can contain any numbers, because we multiply input by some matrix. Numbers can be in any range. And we want ideally for those numbers, we want them to represent probabilities of each class. We want, for example, Z1 to be a probability that the image is a cat, and Z2 the probability that the image is a dog. So to make them probabilities, we need to somehow normalize them, because without normalization, like Z1 can be 5, Z2 can be -5, and we would not know how to interpret that. So to make probabilities out of that, we used a special function called softmax. So softmax kind of makes probabilities in the sense that those probabilities would always add to 1, and they would be all greater than 0. So for example, if Z1 and Z2 is like 5 and 5, probabilities would be 0.5. If Z1 and Z2 is like 10 and 1, the probability would be like P1 would be almost 1 and P2 would be almost 0, something like that. So again, we start with the input vector, we multiply it by weights, we get network output, we run it through softmax, and we get probabilities. And now it's time to train the neural network. And to train it, we need to show it some data, right? So we show it a picture of a cat, and then we expect the output to be 1, 0. But the output is not 1, 0. So we can calculate loss. Loss is something which shows how bad we did. So loss would be 0 if we did perfectly well, and loss would be more than 0 if not. And naturally, what we want to do, we want to minimize the loss. So loss is typically calculated using cross entropy. This loss function is called cross entropy loss. So we can say that loss of the network equals to cross entropy loss of soft masks of wx plus b and y, and we want to minimize that. But how can we minimize that? We cannot vary training sample. Training sample is fixed. We have a certain number of photographs of cats and dogs. We can vary parameters. We need to adjust w and b in order to make neural network perform better. So we need to minimize that by varying w and b. And there is a mathematical process to do that. And we should not probably go into details, but we can adjust weights bit by bit so that the network performs better and better. And to adjust that, we need so-called gradient of loss. Gradient shows how we need to adjust the parameters in order to make the function smaller or bigger. So gradient is actually a mathematical term which is like a derivative of a function with many parameters. So what we need to do if we want to train a neural network, we need to be able to compute the gradients of those operations. And that is what neural frameworks do. So why do we need things like PyTorch or TensorFlow if there is NumPy in Python? For two things. First of all, we want to be able to use GPU. And to use GPU, that's not very easy because you need to, like GPU is a separate processor. You need to put data on GPU. You need to start parallel computations on GPU and then take the data back. So that is not very easy to program if you are doing that from scratch. So frameworks like TensorFlow and PyTorch, they allow you to do that pretty easily. You can say like, I want to compute this on GPU, and pretty much that would happen. And second thing, they perform automatic differentiation, automatic calculation of gradients for you. So you can write an expression. You can say, I want to multiply wx plus b, calculate softmax, calculate loss. And then I want to be able to calculate the gradient of this loss with respect to w. And that would happen. That is not very difficult task. So calculating gradients is just some mathematics, which you need to very carefully write out for all the operations. But definitely it's not fun to do it yourself. And the authors of PyTorch and TensorFlow, they did that. So I'm saying a lot of things like PyTorch, TensorFlow, and so on. What are those frameworks? Those are two most popular frameworks for doing deep learning. Historically, TensorFlow was first. And that's why it's more widely used in the sense that there are a lot of industrial projects and a lot of code written using TensorFlow. And PyTorch is more modern, so that's why it had kind of a quicker start and fresh start, because they took into account some problems that TensorFlow had in the first version, and they came up with a very easy to learn framework, which started taking off very quickly. However, TensorFlow has also a layer called Keras, which is very simplified version of TensorFlow, which allows you to train neural network much easier than both in PyTorch and traditional TensorFlow. So Keras, there is a book called Keras Deep Learning for Humans, because it actually wants to stress that an ordinary person without knowing the term gradient can train a neural network. So that's why TensorFlow with Keras is probably an easier way to start training neural networks. In this workshop, you have the choice to use either TensorFlow or PyTorch. And which one you choose to use yourself when conducting this workshop is actually up to you. Maybe you can ask the audience, but I would probably recommend to stick to one of those frameworks in order not to be kind of showing different examples and different frameworks and get people confused. So I will, in my demonstration, I will start with TensorFlow, and if we have time, I will talk a little bit about PyTorch at the end. So this is the time when you can tell people, okay, let's get to work, go to Microsoft Learn module, and let's start. So as I mentioned, there are two learning paths for TensorFlow and for PyTorch, which are very similar to each other. So essentially, we have started with PyTorch, and then we have taken it and converted it to TensorFlow. So in terms of concepts, they are almost identical. So let's see how that looks like. And actually, in the workshop, let me also show you how the workshop site looks like. So in the workshop library, if you go to this Introduction to Deep Learning for Computer Vision, you have initially, like the very first thing you see is you have the choice of 2 frameworks. And then preliminary learning about neural networks, introductory modules. And then right now the sample of the data set that we will use. And milestone 0 is get introduced to deep learning and start the sandbox. So what do we mean by that? So let's see how the module looks like. So if we go to ak.ms/learn TF is for learn TensorFlow. You see the whole TensorFlow fundamentals learning path. And it contains this very introductory module, Introduction to TensorFlow using Keras. And then this is the one we will be using, Introduction to Computer Vision with TensorFlow. The reason we start with the second one is because the first one goes like deeper into concepts, and it is not likely to bring you to the result very fast. Like classifying cats and dogs is fun, and learning about tensors and differentiation is not. Well, presumably not as fun as classifying cats and dogs. That's why classifying cats and dogs is what we suggest doing in this workshop. So here, this computer vision learn module starts with training a simple traditional dense neural network to classify data, and then goes to convolutional neural networks, the main essence of what we will learn today. So you can actually start from the beginning and go through this learn module together with the audience. It starts with discussing like what are the computer vision tasks, how you can represent images using tensors, and it starts with a data set. So the data set that that is used in this module is so-called MNIST data set. MNIST data set is the data set of handwritten digits like this. And data set of handwritten digits is again not as interesting as cats and dogs, but it is much faster to start experimenting with because it's small and you can get all the concepts pretty easily. So you can go through this, like how the data looks like. We create the train and test data set in the first unit, and then we learn how to train the dense neural network. So dense neural network is pretty much what I have described you up to now. Input image multiplied by weights. So we can see how this works in practice. Like load the data set, then define the neural network consisting of the flattening layer, then dense layer, then softmax, and then output vector. So that is the way we define the model, which is very easy. Like, like the model is just a collection of layers. And because we have just 10 possible outputs for 10 handwritten digits, it would have 10 neurons. And that's it. Then we train it, and then we get output probabilities for each digit. So I will not go through this content because it's all pretty well described in the Learn module. So students can go through this themselves. You can, like if you have really limited amount of time, you can probably tell them like go through this module before the workshop. And they will understand like how this is done. And then the most interesting part is how to recognize something more difficult than a digit. Because the problem with this neural network, when each pixel is connected to a neuron, is that you cannot really handle the situations when the image is in the slightly different position, in the image. When the cat's face is in the corner, or when it's rotated, you can only handle like very well formatted and simple images. And we have the images which are much more complicated. So that's why we will use something called convolutional neural network. And convolutional neural network is different from the simple neural network, is because it can handle the situations like that. So why? What is the main difference? Like when a person looks for a cat, in the picture, he doesn't just look in the center and make the conclusion if it's a cat or not. The person goes through the image. He scans the image and looks for familiar pieces. Like in the cat, we have whiskers, we have eyes which look like cattish, and those are kind of patterns that we are looking for. And we're extracting those patterns, and based on them, we make the conclusion. Sometimes even, we make it explicitly, because there could be cats which do not exactly look like cats, and we start thinking, is it a cat or a dog? Does it have whiskers? Does it have does it look like a cat? Does it have ears like a cat? But normally, we don't think, we just do this processing automatically, but we look for patterns. And convolutional neural networks is a way for a neural network to look for patterns. So it starts with a small window, which goes across the image and detects patterns. So it multiplies by the neighboring pixels. And when it sees the familiar form, there is a kind of spike in the output. So what we normally do, we take different filters, and each filter would go through the image and detect a certain kind of pattern, like horizontal stroke or vertical stroke or some oblique stroke. And then we get a lot of different filtered images, which we can then pass through a classifier. That is the simplest convolutional neural network. In more complex case, we have several layers of convolution. So we extract small patterns, and then on top of them, we extract larger patterns and even larger patterns, and so on. So that is the typical structure of more complex convolutional neural network. We have filters, convolutional filters in the beginning. Then we kind of collapse the image in and make it smaller in spatial dimension, because if we detected a stroke, for example, we have detected that there is something like a angled oblique stroke, and then there is another one which form the cat's ear, for example. Once we have detected the stroke, it doesn't really matter which specific pixel it's at. We can kind of collapse number of pixels and leave the information that the stroke was there. So once we have extracted patterns, we can collapse the image, and then we extract patterns again and again collapse the image until we end up with only like higher level information. Another way to look at it is the following: like at the lowest level, we extract small patterns like strokes, and then at the higher level, from strokes, we combine like higher level patterns of parts of, for example, faces, and then those parts are put together into the complete faces like this. So that's how convolutional neural network works. So let's now apply this knowledge to our case. In the learn module, you can see how this works with digits, with the data set of digits. So we can, to actually start this, we need to start the sandbox. I already have it activated, but if you go for the first time into learn module, it would tell you activate the sandbox. And sandbox gives you this Jupyter notebook where you can play with it and you can put any code here. So we can see how the training works on the normal images. We import TensorFlow. Then the digit data set is available from Keras itself. So it's very easy. We can just say Keras data sets MNIST load data. It loads digits directly. And then when it comes to training the network, here is the simplest neural network: convolutional layer, flattening layer, and dense layer as a final classifier. We can train this model, or we can have the model with several layers, which is more complex. So this is the more complex model: convolutional layer, then collapse in the spatial dimension, which is called max pooling, again convolution, again max pooling, then flatten, and then dense. So let's see how this model gets trained. Sorry, I missed some of the cells, which is something which you should not normally do. I should have trained the first model too. So that is how the training happens. We say in TensorFlow training, the model is very easy. We just say model.fit. We pass it the data, and that's it. Training data and validation data. And right here, we get the accuracy. And you can see that in a few seconds, like in a minute, we get the accuracy of 93%, 97%, and the validation accuracy 98%. So it's quite easy to recognize handwritten digits. And then this is more complex neural network. We can train it, and you can see that we will also probably get reasonable accuracy. Now, it's time to apply it to our own data set. And to do that, we can go to the end of this notebook and start writing code here. And to write the code, well, you have with the workshop, you have the ready example of the complete notebook which you can use, like if you want to show the demo, or if people get confused, or if you get confused. So this is complete notebook which contains the solution. But for students, there are some instructions which they can follow in the workshop, which indicates the most unclear steps. So for example, we have completed now milestone 1. We started the sandbox, and now we need to get the data. And to get the data, we have the code here. Like we just copy it from the instructions, we paste it into the notebook, we run it, and we have the data set sitting here in the sandbox. If we do ls to show the directories, you can see that there is the directory called pet faces. This is exactly our data set. And if we do ls pet faces, you will see that this data set contains subdirectories for each breed of a dog or a cat. So pet faces is not the original data set of cats and dogs breeds, because the original data set called Oxford data set is slightly more complicated. It contains the full picture of the whole animal. But for the first simplified task, we use the pet faces. So we cut out for you only the face of the animal, like this. And that's kind of easier to start with. Okay, now we have the data. Let's display them. To display them, there is a snippet of code here called display images, which is really useful piece of code. I use it all the time myself, and I copy it from one notebook to another. That's why we also have it here. So display images takes the list of images which you can and shows them. So to show the images from the directory, we can use import. So we can use, for example, pil to load the images. We can say from pil import image. That is the way to load a picture in Python. Then to get the images, we can say display images. And let's take one of the directories. For example, cat Siamese. That sounds cool. So Siamese cat. I will load all the images of Siamese cat. That can be done as the list. I would say image dot open. And then because it's in a different directory, I would say pet faces cat Siamese, and then plus file name. And I will do this for file name in os, and I would need to import os. In os list dir. This is the way to list all the files in the directory, and I will put the pet faces cat Siamese here, and I will take only first 5 files. So that's the way to load images and to display 5 files only. So I have forgot the closing bracket probably. Sorry about that. So that's the way to play with the data set to see how it looks like. And you can see the first 5 pictures of the Siamese cat. Okay, we have done now something called getting the data, the milestone 2. And we also need to load the data as tensors, right, together with their classes, to then put it as an input to the neural network. So to do that, we can use built-in functions from PyTorch and TensorFlow. And here in the instructions, it doesn't say like, what parameters to use. People, they need to dig a little bit the documentation to solve that. So in addition to loading, we need to do some other things. So here you can see that images, they are of different sizes and of different aspect ratios as well. Aspect ratios is not like dramatically different, but still they are not like all squared. So that's why we need to do also resizing. So we need to resize all images to the same square dimension. Square is probably the good option because they are mostly square. And then we also need to normalize, because all images are in the 0 to 255 range, all the pixels, and we need to bring them to the range of 0 to 1. So some of that, those things is handled by the neural network framework. Some of those things we need to do like ourselves. So let's, I will not like write the code to save time. I will go to the solution, and I will take some code from here. This solution contains a good way to like display sample of all data set. So we're using TensorFlow as an example. So let me take an example from TensorFlow. So in TensorFlow, there is a function called image dataset from directory. So the way it works is that we specify the directory, and this function assumes that all files in this directory are in subdirectories according to class names. So it automatically fetches the class names, and it converts images to the specified size, so we can pass the image size. And then we want the dataset to be split into two parts: the training dataset and the test dataset. That's normally what we do when we solve any machine learning problem. And this split can happen automatically, like TensorFlow can do it for us. We just need to say validation split. And then in the function, we provide subset equals training or subset equals validation to return the corresponding subset. So what I do in this clever code, this code is maybe too clever. I mean, like, person seeing this for the first time probably would write it in slightly different way. But what I do here, I create a list of two things, like one is for training and one for validation. And for each list, I call this preprocessing image from directories function. So there is another way to do it. I can say, for example, train equals this. And instead of S, I would put train training. And then the same piece of code for testing. But that is kind of a longer way to write it. Right? So I prefer to do it in a shorter way. So I would comment this out, just like it's possible to write it in this way, but not necessarily. So if we run it, you see that it automatically like found the images and found that there are 35 classes, and we can say like class names equals to train class names to see what are the names of the classes. And here are indeed all our directories here. So let's define also a variable called num classes equals to len of class names, which would contain the number of classes that we want to use for classification. Then the next thing is we need to scale down the images. And that is because those images are in the range from 0 to 255. So I can say train 0. So we cannot do it like this because train is a data set, so we can only iterate it. So to show it, we can do something like this. For xy in train, print xy, and then we can do break. That's the easiest way to iterate the data set. And you can see that here the first thing is the image itself. It's not really obvious that it's an image, but you can say it's a tensor, like a matrix, the picture. And then so there are. So what this function does, it also does mini batching. So here we said batch size equals batch size. Batch size is 32, so it returns us 32 images at a time. So the first thing here, x, is 32 images in a row. And then y is the result. Like for each image, we have the number of class. If I scroll down to the very end, you see this vector contains number of classes. Like the first image is class 17, second image is class 17, third image is class 4, and so on. But what's important here is that images, the pixel values are from 0 to 255. They are not from 0 to 1, and we need them to be from 0 to 1. So that's why we need to make one more pre-processing step and to divide the values by 255. So this can be done using train.map. So it might look a little bit difficult for you in the beginning, but in the workshop, you see, we tell about each step in more detail. We say normalize all images, assuming that all intensities are in the range of 0 to 255, divide them, by 255. So it's presumably like people can understand how to do that, but they need to do a little bit of research. So then in the next step, we need to define actually the neural network. And defining a neural network, well, the easiest way to do it is to go above, because in this notebook, we have already defined the neural network for classification of images and even classification of those kind of more complicated images of different objects. And here is the architecture of a network. So we can take this one. This one is a little bit more difficult, more complex. It has more layers, but yeah, we can take this one and start from it. So I basically copy the code. I need to make sure that input shape is correct. So in my case, I scaled everything to image size. So I need to put here image size by image size. And the output should contain number of classes. So here, instead of 10, I would say num classes, and I will probably skip one of the dense layers because it's a little bit too much to have 3, but that doesn't really matter. You can try different architectures here. So now we have the neural network model defined, and we can start training it. Let's see in the library, we are now at the milestone 3, define and train neural network. So it tells you more or less like the things you need to pay attention for. The main difficulty here is to find the right combination of loss function and activation function at the last layer. But here it says that, for example, in TensorFlow, you can use softmax as activation function and sparse categorical cross entropy as loss function. So what does it mean, sparse categorical cross entropy? You can put the expected output of a neural network in different ways. Because in the picture that I have shown you before, if we have like 35 classes, the network would have 35 outputs. And the expected output would be, like, for example, if it's the breed number 5, the output would be 0, 0, 0, 0, 1, and then 0, 0, 0, 0 again up to the end. So this is called one-hot encoding. So we need to calculate the loss function between this vector and the output of the network. However, it is much easier to pass the number just as number 5, not as this vector 0, 0, 0, 1, 0, 0, 0, 0. And that is what sparse categorical cross entropy is for. We use sparse, indicating that instead of this long vector of zeros, there would be just a number as the expected output. And as we have seen before here, this is exactly the format that we have. We have the vector with numbers and not with zeros and ones. So that's why in our network, here we need to use sparse categorical cross entropy and softmax. So softmax activation function is defined here, and the loss function is defined during model.compile. So here we say again model.compile. We can take the example from above because we are essentially writing the same code as here in the module. So that is how the model training looks like. I will just take the code from here verbatim and put it here. So again, essentially what we are doing, we are repeating the module. In the module, we train the network on simpler images, but now we are taking more complicated, more real-life images of cats and dogs, and we are training the model on those. So here, again, you see that it's already sparse categorical cross entropy here. And we just need maybe to adjust the names of the data set because in our case, data set is called train and text and test. So here we say train and validation data equals test. And number of epochs, I will make it 3 in order not to wait for a long time. And now the training starts. We can see immediately the accuracy that we are getting. At the first pass, it's not really high, like 22%. But remember that even 22% is pretty good because we are classifying out of 35 classes. So if it was a blind guess, the probability would be like around how much? 0.03 or something like that. So in three epochs, we get something like 40% of validation accuracy, which is like not too good, but we can continue training for more. It also makes sense to print out the graph, which would look somehow like this. And it would show that training accuracy always goes up, and validation accuracy on the validation data set, it stops raising at a certain point. And that is called overfitting. Because what happens here is that if we take a large model, we would always be able to achieve very high accuracy on training data because the model looks at the same examples over and over again with each epoch, and it kind of learns them by heart. But new examples that it doesn't see, they are more challenging. And that's why the model kind of understands certain important features, but only to a certain extent. And then it cannot like generalize even more. And in most of the cases, what you will see that accuracy starts to drop after a certain point. And that means we should stop training. We have the overfitting. So that is the main part of the workshop, which is already like we have already solved a relatively complex real world problem. What else can we do? It's interesting to see like the accuracy of 0.5 doesn't look very impressive because like, you know, like 50% as the accuracy doesn't sound right. But what does it mean? We are now classifying between different breeds of animals. And if you ask a person, a human being, like which breed of a cat is that, you would probably not get like an accurate result. In many cases, people will confuse different breeds as well. And that is quite normal because they are very similar, some of them. So that's why in when you have the situation like that, when you have many classes and some of them are similar to each other, you want to calculate instead of accuracy something called top K accuracy. So top K accuracy, for example, top 3 accuracy is when I take top 3 results of a neural network, would the expected class be within them? So by top 3, I mean top 3 most probable results, because neural networks gives us probabilities as outputs, right? So it will tell me it's the Siamese cat with the probability of 0.6, and then it's the like another British cat with a probability of 0.2, and then, you know, something else with probability of 0.1, and even maybe a dog with a probability of 0.001. So we want to make sure that if it's British cat, that this British cat is within top 3 probabilities. And that is a much better metric, because it will show that our model, like, even if it does a mistake, it doesn't make very large mistake. It only misses like a class by a little bit. So to calculate this top K probability, we need it's actually quite a tricky thing, and that's why it says optional in the workshop, because you need to look on the internet a little bit for the solution. That's not like very easy thing to do, but it shows where to look. It like in the workshop, it says to calculate top K accuracy, you need to use TFNN in top K function in terms of flow. So there is a starting point, and then you need to go and dig a little bit deeper. So let's see in our case what is the probability here. You can see that it's 67%, which is like not too bad. So that is the main part of the tutorial. But then there is another part. Like if you are running the tutorial for 1 hour, probably there is no chance you can go further than this. If you are running it for 2 hours, then you can also do the next step. And next step is much better. It gives much better results. So what do I mean by that? In real life, there are many cases when we do not have large data set, but we still want to solve our problem. Even this PET data set, it contains only 200 images of each class, which is not a lot. So in real life, we use an approach called transfer learning. So transfer learning, I'm showing the presentation slides, which I kind of missed. Sorry about that. And then there are also questions that you can ask your participants after they complete something. So for example, what we have learned, what is a convolutional layer? It's the layer that runs a small window across the image to extract patterns. So in the presentation, you have slides which allow you to do this kind of quiz, interactive quiz with participants. So this is already the time to congratulate everyone, but then we have the second part, which is recognizing real world images, which look like this. You see, they are much more complex than the previous ones, but to recognize them, if we try to apply the same approach, we will get very low accuracy. Like if you try, the accuracy would be something like 20%, which is like really, really low. We want to do much better than that. And in order to do that, we use the tricky thing called transfer learning. So transfer learning is when we take the pre-trained model, like somebody trains the model on a very large data set, and the model learns to extract different patterns. Because as we mentioned, convolutional neural network is good for extracting patterns, but patterns in many objects, they are like very similar, right? Especially low-level patterns like different strokes and different different small textures. And we can train the model on a huge data set of real world images like ImageNet, and we will end up with a trained model which is able to extract patterns from the image very well. So what we can do, we can take this pre-trained model, apply it to our images, extract patterns, and then classify only those patterns, train only final layers of the neural network, which would classify into the classes that we need. So we will take the pre-trained top of the network and then retrain the bottom. So this is the approach called transfer learning. It sounds a little bit complicated, but it's quite easy to implement. I will probably not have time now to show it to you. Let's see. So I will start with the solution notebook. I will just show you the solution notebook. It loads different data set, and the initial steps are all the same. Now let's display this data set. Here are the images. Let's resize them. And here is the tricky thing. When we resize the image, there are different options that we can use. So for example, here we choose to distort the aspect ratio, right? Because if the image is not square, then we have to somehow fit it into square. So distorting the image is kind of the easiest solution, but probably not the best one. Probably ideally you should like do something else, like leave the original aspect ratio and leave padding around it. So you can take some time to discuss those different approaches as well. Then if we do like the neural network like we did before, the accuracy would be, this is the example that I run, so 14%, better than blind guessing, but not much better. This is the graph. So for transfer learning, what we need to do, we need to use this pre-processing layer as the pre-trained network. So we will use the network called ResNet 50. ResNet 50 is the network, like large pre-trained network introduced by Microsoft Research in 2015. So our neural network would look like this. The first layer, we will do pre-processing because each pre-trained network requires its own pre-processing. By pre-processing, I mean steps like normalizing the image so that inputs are between 0 and 1. But in some cases, like we want them to be from -1 to 1, for example. In some cases, we want to like increase the contrast of the image or something like that. So each pre-trained network was pre-trained on certain pre-processing steps. So that's why it's good to use the same pre-processing steps, and that's why Keras has a special function pre-process input specifically for this ResNet 50 model. So the first layer would be this pre-processing step, then we would apply a ResNet model, and then there would be a final classifier. And one more thing, so this network is assembled from different layers. One of them is pre-trained layer, and we do not want to retrain this layer. So that's why we set this trainable to false. And then we do the same kind of model.compile and model.fit. That would take a little bit more time to run because, well, this model, ResNet 50, is a really large model, and you need, you know, it's like heavy, and that's why it's not very fast. But at the end, you would be able to achieve 84% accuracy of specifying the breed on this very complex data set of images. And if you take top K accuracy, top 3 accuracy, it would be 96%. So that would be like real, I think, nice thing for people to reach this accuracy, because that is something you can really put into an application. So the important thing to note here is that for transfer learning especially, we need GPU-enabled compute. So we cannot easily run this workshop on like on a personal machine. Why? Because it requires the GPU. So Microsoft Learn Sandbox has the GPU support built in. So that's why it is really highly recommended that you start the Learn module. You go through like the initial some initial content in that Learn module, and then you use the same sandbox with GPU to run to actually put your code there and run the workshop. About transfer learning, I wanted also to show you that here in Learn module, we have the next section, which is called transfer learning. So if you switch to the next section, to the next unit here, it's called pre-trained models and transfer learning, and it contains all the required information here as well. It tells you like you know, like how to do pre-processing and how to load images and so on. It actually takes also the data set of cats and dogs, but much simpler data set than the one that we have used, and shows how to use it for classification. So you can also like tell your participants, you can leave this transfer learning as the home exercise, for example. You can say, go through this next unit, train the model, train it on the data that is provided here, and then adjusted to the data set that mentioned in the workshop. That is probably like a good homework, good as a homework exercise. So once you have done that, once you have trained the model to achieve 96% top 3 accuracy from 37 classes, what can you do next? There are a few things you can do next. First of all, it's interesting, how would you put this into an application? Like how you can make mobile application that classify cats and dogs. And normally it would require like putting the model inside the cloud to be able to run as a service. And this can be done either in the Azure function or in Azure ML cluster. And there are learn modules which describe how to do that. So that's one of the directions you can continue learning. Another direction is how to create an application which would do the inference locally on the mobile device. And you can do that. You can use lightweight architecture called MobileNet to do local inference on local device. And finally, there is a third direction you can go. You have learned how to deal with images. You can continue and learn how to deal with text. And there is another workshop on text. And there is, again, corresponding learn module on doing text classification with both PyTorch and TensorFlow, which is the natural continuation of this learn module about images. So that is the introduction to deep learning workshop. Let me know if you have any questions. I'm ready to answer them. Any questions, folks?
Hello, Dmitry.
Hello.
Yeah. So it's Eric. So first foremost, great presentation there. Sorry I lied a little bit late. So I had a question because I've heard you mention about transfer learning and everything. So I was wondering what would be the difference of doing it with convolutional neural networks instead of transfer learning?
Transfer learning actually is a convolutional neural network. So the main idea of transfer learning is to take the convolutional neural network, which was trained on the different data set. So somebody trains the model on the huge data set. We take this model and use 99% of this model and only replace the final classifier. And actually, it is important that it's convolutional neural network because only convolutional neural network can extract those kind of visual patterns. And that's why, because visual patterns are similar between different objects, that allows us to do transfer learning. If it was not convolutional neural network, it would be impossible to do transfer learning.
Okay, Dimitri, makes sense. Thank you so much. Thank you so much.
Thank you. Nice to see you here. Okay, if there are no questions, feel free to leave any feedback, like was it unclear, was it clear? You can do it to me directly, or you can let me know in the chat or in any other ways, because we are always looking to improve things. And that's why we desperately need to have the feedback from real people, because yeah, that is really important for us. If you run the workshop on your friends, definitely encourage them to fill in the feedback forms, because we always process the feedback from the feedback forms, and we are improving the workshop as we go based on that feedback. Okay, it was nice seeing you here, and yeah, join us for more workshops. You have a lot of content now which you can choose from. Thanks again, and have the great day, evening, whatever time it is there. Thank you.